How we doing, everyone? We're looking at related rates of change. Or really what we're looking at in this section is the chain rule, or an application of the chain rule. The chain rule in its formal version would say dy dx can be broken up into dy du multiplied by du dx. Now that's not what we saw. What we would have said is, if this is a function y, the chain rule says differentiate as usual, ignoring the bit in the brackets. So 5 times this to the power of 4. Okay, and then we said multiply by the derivative of this thing. So 2 times 2 is 4x. Okay, so that's how we would have differentiated using the chain rule. A more formal way to do it is to call this thing u. So u is 2x squared plus 3. And so y can be written now as u to the power of 5. And dy dx is then dy du multiplied by du dx. Okay, well, what's dy du? That is 5u to the power of 4 multiplied by what's du dx? That's going to be 4x. And rewriting that, 5u to the power of 4 multiplied by 4x, and we know that u is 2x. 2x squared plus 3. Okay, you can see there, it's the same answer as up here. Okay, so that's just maybe the more formal way of following through on the chain rule. And I emphasize it because we are going to need this kind of rule an awful lot. And what I want you to notice is the pattern here. It's kind of like you've got a common factor of du that you're introducing. You're separating out dy and dx and introducing some third variable, du top and bottom. Now, that's not quite what you're doing. These aren't fractions. But if you think about it that way, it'll work out for you. That you've got this thing you're multiplying, I'm doing air quotes, multiplying top and bottom by du there. The second thing I want you to answer, and I want you to pause the video to answer this one. If you fill a barrel at a rate of 5 liters per minute, so the hose is producing 5 liters per minute of water, the height of the water in the barrel rises at a rate of 2 centimeters for every liter you add in. At what rate is the height rising per second? Okay, so can you just pause there, answer that? Okay, hopefully you've done that. If you got an answer of 10 centimeters per second, you're spot on. Okay, what you would have said was 5 liters per minute multiplied by 2 centimeters per liter. Okay, and look what happens. You've got this common unit of liters top and bottom, gives you 10 centimeters per minute. Okay, but what you're looking at here is related rates of change. Related rates of change. The rate of change of volume with respect to time, that's dv dt multiplied by, this is the rate of change of height with respect to volume, dh dv. And much like our chain rule here, look, you've got this common dv top and bottom. And what did you get? You got dh dt. You got these bits left over. Okay, so really what we're doing in this is we are converting exercises like that. We're applying the chain rule to convert one rate or one pair of rates maybe into a third rate. Okay, so these are related rates of change. We're going to start off looking actually at a tricky enough one straight away, which is question 12, just to get the ideas really fully in there. Okay, so a pump is inflating a spherical balloon. The radius of the balloon is increasing at a rate of 1 centimeters per second. So there's our first rate that we need to work with. Okay, the radius is increasing. That is dr, the rate of change of the radius per unit of time. So dr dt when the length of the radius is 2 meters. Find the rate at which the pump is working, the rate of change of volume. Now, rate left by itself will always mean with respect to t. So the rate of change of volume is with respect to time. Find dv dt. Okay, so we were given in this question that dr dt was equal to 1 centimeter per second, and we were asked to find the rate of change of volume dv dt. Now, if you think of our chain rule, we always had 3 rates. whereas here we've only got 2. So how do we fix that problem? Well, we know that it's a spherical balloon, and we know the volume of the sphere is 4/3 pi r cubed. So actually, the third rate we want is one that relates volume to radius, dv dr. So we can find that by differentiating here. dv dr is going to be 4/3 pi. Bring that 3 down, you get 12 pi r squared over 3, or 4 pi r squared. So now we have dv dt. Using our chain rule, we can separate that out, introduce this new variable r, dv dt, and we say we want to introduce this variable r, dr and dr. Well, dv dr we've just worked out. It's 4 pi times the radius squared multiplied by dr dt. We were given up here 1 multiplied by 1 centimeter per second. Okay, and we know as well from this question, sorry, I should have included this at the top, that the radius is 2 meters at the point that they're asking about. So that means we can say 4 pi times 2 squared times 1, and we get 4 times 4, that's 16 pi. Rate of change of volume with respect to time, that's centimeters cubed per second. Now this is just at that time when the radius is 2 centimeters. At a later point, and the increase in volume with respect to time might be changing. Oh, sorry, that's not true, because it's a pump. The pump is pumping the same volume in the whole time. Part 2 says if the air continues to be pumped at this rate, so this is the rate that we're pumping air into our sphere, find the rate of change of the radius when it is 5 meters in length. So again, the rate of change of radius means the r dt. Okay, so it's always with respect to time. So our chain rule, we can break that up, dr dt. And what is our new variable we need to introduce? Well, that is volume. Okay, so we're going to introduce dv and see if we can come up with these rates. Well, dv dt is what we just worked out. That's 16 pi. So that's no problem, that second one. This first one, the rdv, we don't know that one. We do know dv dr. So let me come back over here. If I'm filling a barrel at a rate of 5 liters per minute, okay, that is dv dt. And if I asked you at what rate am I filling it, how many minutes per liter, okay, the answer would be, well, it's 1/5 of a minute to fill 1 liter, 1/5 of a minute per liter. That's the rate at which you're filling it if you're saying time with respect to volume. Okay, how long does it take to get 1 liter? 1/5 of a minute per liter. All I've done is inverted. Likewise here, the height rises at a rate of 2 centimeters per liter. That's dh dv. If we're doing it the other way around, is 2 dv dh. The rate at which the volume changes with height is 1/2 of a liter for every centimeter that it rises. Okay, so you can invert a rate just by flipping it upside down, by flipping the fraction as it were upside down. 2/1 becomes 1/2. So dr dv, well, we have dv dr. So dr dv is just 1 over that. It's going to be 1/4 pi r squared. dv dt, we know from down here, is 16 pi. And so what is our rate of change of radius with respect to time? Let's see, pi cancels, 4 cancels, and we're left with 4/r squared. And the question was when it is 5 meters in length. So dr dt is 4/5 squared, 4/25, or 0.16. Rate of change of radius with respect to time, that's the distance, centimeters per time is second. Okay, so 0.16 centimeters per second. And then at what rate is the surface area of the balloon increasing when the radius is 5? Okay, so find dA dt when the radius is 5. So again, you're going to say, well, dA, introduce some other variable. This time, the one that's going to be useful to introduce is the radius. Why? Well, we know a formula for the surface area of a balloon. Surface area of a balloon is given by 4 pi r squared. So that's the area in terms of the radius, or as a function of the radius. So if we say, sorry, this is a little bit untidy, but if we say the area is 4 pi r squared, then the rate at which it changes with respect to the radius is going to be 8 pi r. Okay, so we can come over here and say dA dr is what we want to work with. Dr dt, we already know. That's what we just worked out up here in part 2. Dr dt is 0.16. Okay, so we say dA dr, the rate of change of the area with respect to the radius, is 8 pi r. Multiplied by dr dt is 0.16. And this is when r is 5. So that's going to be 8 pi times 5 times 0.16, which gets us 6.4 pi. The rate of change in area with respect to time, so that's centimeters squared for area with respect to time is seconds. Okay, that's question 12. I think I probably dove in fairly straight away into quite a tough question there. So I'm not going to do another one. I'm actually just going to ask you guys to have a look at question 9. See if you can do it. Okay, maybe spend 10 minutes out of your, or 15. And if you're stuck, then don't worry, we'll have a look at it tomorrow. Okay, see you tomorrow.